In this presentation, we will talk about waves, the different types of waves that we have, and then eventually we will talk about sound. So there's lots of different types of waves. Some of them we're familiar with are waves that are in water, waves that travel on a string, like if you had a guitar and you were to pluck the guitar. You can have waves that travel in a column of air, like a musical instrument such as a flute. Some other waves that you may not be familiar with are sound is actually a wave, and light is a wave as well. So we're going to talk about these different types of waves. And so the first thing we have to do is we have to define the fact that there are two different types of waves that we can classify all waves in terms of. A wave is either a mechanical wave or an electromagnetic wave. Mechanical waves have to have some type of a medium to travel through. So for example, a water wave needs the water to travel through. Sound is actually a mechanical wave and it needs air, for example, as one possibility to travel through. Waves on a string, that's a mechanical wave. The wave is actually traveling on a string and so on. Electromagnetic waves are different than mechanical waves. They don't need a medium to travel through. They can actually travel through the vacuum of space. And we'll talk specifically about electromagnetic waves in the future, but electromagnetic waves are waves such as radio waves, light, X-rays. There's a whole spectrum of electromagnetic waves. So in this presentation, we're mostly going to focus on mechanical waves, but our description of waves actually takes into account all forms of wave, both mechanical waves and electromagnetic waves. So a wave is a traveling disturbance or a traveling vibration. And in mechanical waves, the medium itself does not actually move from one location to another. It's just the wave or the disturbance that actually moves. So as an example, waves on a string, the string actually vibrates at one location and then that vibration travels down the string to another location, like on a guitar. Let's take a look at an example of a wave that is traveling in water, or a pulse that's traveling in water. So here, if I were to have, this is like a faucet and then there's a container of water. If I go ahead and I drop some water, it creates a disturbance in the water, and that disturbance travels along the water. The water itself doesn't physically move from one place to another. It's the disturbance. So the water was disturbed, and that disturbance travels through the water. So waves can just be like a pulse. In that case, that was a pulse wave, or they could be periodic. They could repeat themselves. And so here, the drip is going to keep occurring at a particular pattern. And as that happens, we can see that the wave continues. It has a pattern associated with it. They seem to all be about the same size and separated the same distance, and it's repeating. So waves can be periodic. They can have a regular pattern associated with them. One of the other things is that the medium returns to its undisturbed position after the wave motion ceases. So again, if I go back and I turn off my faucets, the drips, the medium goes back to the undisturbed position. So all waves, regardless of whether they're mechanical waves or electromagnetic waves, have some source of vibration that's actually creating that disturbance. So we've got these two different types of waves, mechanical waves and electromagnetic waves, and then we can classify waves into two different types. The wave classifications are either transverse waves or longitudinal waves. So with a transverse wave, the disturbance of the wave is perpendicular to the direction that the motion that the wave travels. So here I have like a slinky or a spring, and a hand is disturbing that spring up and down, so in the up and down direction, but the wave itself, or the traveling disturbance, is moving to the right. So the wave is traveling horizontally and the vibration occurs perpendicular. So transverse waves, that disturbance is going to be perpendicular to the direction of the motion. But notice that the medium goes back to its undisturbed position, right? So it's undisturbed, and now the wave is traveling to the right, but then the medium goes back to the way that it was after the wave or the disturbance passes by. With a longitudinal wave, the disturbance is parallel to the direction of the motion of the wave. So here the hand is moving along the horizontal direction, and the wave is actually traveling along that direction as well. I can follow the wave or the disturbance going down. So here it is traveling down. But of course, once the disturbance stops, everything goes back to the undisturbed position as well. So longitudinal waves, disturbance is parallel to the direction of the motion. So here's a picture of both of those waves together so we can see the difference. The disturbance here, of course, transverse is perpendicular, up and down. Longitudinal, it's back and forth. But in both of these pictures, the medium goes back to the undisturbed position after the wave passes or that disturbance passes. So there's different properties of waves as we talk about waves, and this is actually true of a transverse wave or a longitudinal wave. And so the first thing that we could talk about in terms of the property of the wave is the amplitude of the wave. So the amplitude is the maximum disturbance from the undisturbed position. So here in this bottom picture, we can ignore the one that's repeating right now. But in this picture right here, the undisturbed position is the green dotted line. And then basically we have like a string, and it's being oscillated up and down here by a spring. And this is the wave as it would be traveling. For example, there's an arrow that's showing it traveling to the right. So it's basically this picture right here, but it's a snapshot of this picture. So we've got the oscillation up and down, and then we've got the wave that is traveling to the right. So the amplitude is just the distance between the undisturbed position and whatever the maximum disturbance is. So here would be my amplitude in my picture. The wavelength is the distance between successive crests or troughs, or basically the length of one complete cycle of the wave. So in my picture that's not moving, here is the crest of the wave, and then the next crest occurs over here, and so my wavelength is just the distance between successive crests. I could also go to the troughs, which is the lowest point, and I could measure from here over to here, and that would be a wavelength. Or basically any distance where I get to the same point in the wave before it starts repeating itself. So here's also a wavelength here, starting and then coming back here. The frequency is the number of repeating cycles of the wave that occur every second that goes by. So basically, if you were to take a stopwatch and you were to count how many times, like for example in this oscillation going up and down, you would have to count the number of repeated cycles that occur in 1 second. And that would tell you the frequency. So if this is oscillating up and down faster, that would have a bigger frequency. There would be more repeating cycles per second if it was traveling up and down faster. Higher frequency. If it was moving slower, then it would have a slower frequency or lower frequency. So it turns out that in terms of definitions and units, 1 vibration per second is equivalent to what's called a hertz. So if you hear the term hertz, that's the unit for frequency. Wavelength is a length, and I didn't put units here, so it can be any units of length. So it could be measured in meters, centimeters, it could even be measured in feet. And amplitude is also a distance, so that could be measured in meters, centimeters, feet, and so on. In physics, our standard unit for length would be the meter. And then finally, we have the period, and the period is basically the time it takes to complete 1 cycle of the motion. So here I would take a stopwatch, and I would time how long it takes to start here, go all the way up, come all the way back down to where it started again, and that would tell me what the period of the motion is. One thing that's nice about this particular picture is we can see how the wave travels during 1 cycle, how far it travels. So I'm going to let it go through this cycle again with this transverse wave, and when it gets back over here, we're going to look at that wavelength, and we're going to see how far it travels when this goes up and down 1 whole time. It goes all the way over here, it has traveled 1 wavelength. So we're going to explore that a little bit more. let's consider one of the Phet simulations and see if we can explore some of the different properties of the wave. So we're going to open up the wave on a string simulation. We're going to set the damping to none. We're going to cause it to oscillate and not have an end. And we're going to determine using sort of this step forward option, which I'll show you. We're going to determine the amplitude of the wavelength, the period, and how far the wave travels during one period of the motion. So I'm going to hit end here, and we're going to go ahead. So here is the Phet simulation. And so the first thing I'm going to do is I'm going to say no end. So it basically lets the wave travel without reflecting back, because waves can reflect off surfaces. I'm going to hit oscillate, so it causes an oscillatory motion over on one end. And right now this wave is damped, so you'll notice, let me slow it down, you'll notice that the amplitude over on the left side is higher than the amplitude over here because of basically friction. So I'm going to come over here and I'm going to convert the damping to none. I'm going to go ahead and put it back to the normal cycle, although it is a little disturbing, so I'm going to pause it. I'm going to go ahead and put the rulers on, the timer, and I'm also going to put a reference line. So this reference line is something that can be moved up or down, and essentially it allows you to mark a place on the wave. So I'm going to mark the maximum position, and I'm going to about the center of the, like I don't want to go to the top, I'm going to go to about the center of these beads that are on the string. And then I can measure the amplitude, which is the distance from the undisturbed position, which is the dotted line here, up to the new dotted line up at the top. So if I go ahead and I set this up, I measure that distance to be so at the 0 mark, each of these divisions is 0.2 centimeters. So I have 0.2, 0.4, 0.6. It's not quite 0.8. And it's a little bit more, 0.7 would be right in the center, so we would estimate that, I'm going to say that it's close to 0.8, right? So it's 0.75, which is what the amplitude is down here, which is what we would expect the amplitude to be because we set it that way. If I adjust the amplitude, I have to hit play, right? Let's pause it again. Obviously, this has a larger amplitude. Now I'm going to go ahead and I'm going to put this back to 0.75. And I'm going to hit play again, and now I can pause it. The other thing that we're asked to do is we're asked to measure the wavelength. And of course, the wavelength is the distance between successive crests or troughs. And so one of the nice things about this Phet simulation is you can actually step it forward. So in this case, I'm actually going to step it forward quite a lot there. And there are some green beads that are on the string. I wouldn't worry too much about those. They're not really, they're just a reference to show you different positions on the wave, so don't worry too much about those. So I want to measure what the wavelength is, and the wavelength is essentially the distance between successive crests. So here's a crest, and I have put it on 0, and then here's a crest over here somewhere. It's probably right here, so I would probably say that's about 4.1 centimeters, because remember each one of these is 0.2. So I would say the wavelength is 4.1. I could measure from trough to trough. It's a little harder to do that with the way this simulation is set up, but I could certainly go forward with it. And if I wanted to, I could have measured the distance between the troughs. Again, this one is a little harder just to set up, but it should give me the same thing. So here it's 0'd at the trough, and then down here would also be 4.1 centimeters. The next question was to measure the period of the motion, and so I have a stopwatch here, or a timer. The problem with trying to use the timer and starting and stopping it is that if you do it when you have it in the normal mode, it would be impossible to start it and stop it. So the best thing to do here is to just find a good reference point. Okay, I'm going to actually start it at the 0. And I'm going to step it forward until it goes through one complete cycle. So all the way down and all the way up. Now, the other thing I want you to do as I'm going through that is I want you to take notice of where the wave is right now. So the top of the wave is currently right here, right? It's starting right here. Notice where that wave ends up after I go through one cycle, and that will answer 2 questions at the same time. So I'm going to hit the start button on the timer, and I am going to step this forward, and as I step it forward, the timer will keep track of the time. So it's just doing like a slow motion thing. So here we go. I've gone all the way down. I'm heading back up. Notice, here's my wave right here, right? It was over here when I started, and now it's over here. I've got to keep going. I haven't gone through one cycle yet because I have to go all the way up. Here I am, all the way up. Here's my wave where it was over here. Come all the way back down again. There we go. And my wave is now located, it started here and it ended up over here. So in one period, I've measured my period, which is the time to basically go through one cycle all the way up and all the way back down. My period was 0.66 seconds, and the distance that the wave traveled was from this location, the 0 point, all the way over to here, which is 4.1 centimeters. Well, you may remember that the distance between the two crests, and we can see that right here, is 4.1 centimeters. So a wave will always travel a distance of one wavelength in a time of one period. And that's important as we continue to talk about waves, and eventually we'll talk about the speed of a wave, and that, of course, speed is, you know, how far does it go and how long does it take to travel that particular distance. So as a reference, there's some pictures of basically what we just did in the simulation. There's that distance with the reference line, that 0.75 centimeters. And then our wavelength over here, right, which is about 4.1 centimeters in our picture. So these pictures are measuring things slightly different than the way that we did it in the simulation, but it still basically works the same way. We're getting the same values.